You're in bed, the room is pitch black, and you glance at your phone. In a fraction of a second, the screen glows and unlocks. If that was a standard camera lens trying to see you, the image would be unusable. Traditional cameras depend on visible light particles bouncing off physical objects. Without them, the sensor captures only noise. Even with the lights on, standard photography has a major security flaw. It takes our three-dimensional world and flattens it into a 2D image. Because it lacks depth, a standard lens can be fooled by someone holding up a printed photograph of your face. To build a secure biometric lock, engineers had to move beyond traditional photography. They needed a system that could see in total darkness and, more importantly, understand depth. This diagram shows the shift in strategy. On the left, a standard LED emits visible light for the human eye. On the right, an IR LED emits infrared radiation, light existing just beyond what we can see, easily detected by specialized camera sensors. By equipping the phone with an infrared projector, the device provides its own consistent, uniform illumination. It bathes your face in light that is invisible to you, but incredibly bright to the phone's internal sensors. Migrating out of the visible spectrum gave devices a controlled environment to operate in the dark, providing the foundation needed to measure physical space. To see how this works, we have to slow down the single millisecond it takes to unlock the phone. It begins with the flood illuminator. The moment you wake the screen, this component fires. It washes your face in a broad beam of infrared radiation, so the camera can see you clearly, even in a windowless room. A fraction of a millisecond later, the second hardware trigger fires, the dot projector. Using a technique called structured light scanning, the projector casts a rigid grid of over 30,000 distinct infrared dots across your features. Look at how the grid reacts to the face. When those uniform, straight lines of light collide with your physical features, the bridge of your nose or the curve of your cheeks, the grid is forced to bend and distort. This distortion is the vital link in the process. It is the physical mechanism that translates a flat visual feed into a readable map of your facial geometry. The third component, the infrared camera, captures this distorted pattern to execute a mathematical depth calculation. The system measures the microscopic distance between a dot's expected flat surface landing and its actual reflection off your face. This disparity shift calculates exact depth. Running this simultaneously across 30,000 points generates a high-fidelity 3D wireframe of your face. This mathematical map is securely routed to the final step, the device's isolated neural network. The AI compares this spatial data against your encrypted profile. Because the infrared camera picks up the high-contrast reflection of moisture on your eyes, it can also verify that you are awake and actively looking at the screen before granting access. In a fraction of a second, the system moves beyond matching a simple picture. It completes 30,000 geometry problems and performs a behavioral audit. The entire sequence, the flash, the grid, the triangulation, and the AI audit, is completed in the time it takes to blink. This reliance on depth mapping is what prevents unauthorized access using printed photos or digital screens. If you hold up a photo, the dots hit a flat surface and create zero distortion. Without that physical shift in the grid, the math fails and the phone stays locked. Because this technology is so difficult to fool, infrared depth mapping is moving beyond smartphones and into high-security transit checkpoints and automotive safety systems. Your device is no longer just taking a picture. It's using invisible light to map your physical features into a precise 3D model.